Hello all. In this video we will describe the stochastic gradient method and look at its intuition as well as some history. The stochastic gradient descent updates take the form xt plus 1 equal to xt minus eta t into gradient of f at xt comma xi of it, where it is a randomly chosen index from 1 to n. In other words, each iteration of stochastic gradient descent corresponds to selecting xi of it at random and then calculating the gradient of that component. A few key things to note about the stochastic gradient descent are: first, that it is random, therefore the iterates xt are also random. And in fact, you can verify that the sequence xt of the iterates form a Markov chain. Then the second is that minus of the stochastic gradient, which is minus gradient f of xt comma xi of it, is not a descent direction. Thirdly, since it is picked uniformly at random from the index set 1 to n, the expected value of the gradient is given by expected value of gradient f of x comma xi of it for a given x is equal to 1 over n summation from I equal to 1 to n gradient of f of x comma xi I, which is equal to gradient of capital F of x. So we can see that we are going in a direction that is the descent direction on average or in expectation. Finally, note that the expectation here was taken with respect to the random quantity it, and this equation only holds for a given x, not for the iterate xt. In other words, the expectation of gradient f of xt comma xi of it is not equal to gradient of capital F of xt. This is because xt is random and the right hand side in this equation is also random, while the left hand side is not random because we have taken the expectation. We can also consider a hybrid of the stochastic gradient descent and gradient descent, which is called the MiniBatch stochastic gradient descent. Here, instead of selecting a random it, we select a random subset calligraphic I of t and carry out the updates xt plus 1 equal to xt minus eta divided by the cardinality of calligraphic I of t, summation over all I in calligraphic I of t, gradient of f at xt comma xi of I. So here, if the cardinality of I of t is equal to 1, then this would become the stochastic gradient descent. And then if the cardinality of I of t is n, which is the size of the data set, then it becomes the gradient descent. Typically, we set cardinality of I of t to be something from 16 to 64, maybe even 128, but rarely larger than that, which is usually much smaller than the size of the data set n. So the advantage of MiniBatch comes due to parallelization. You can write the code in the vectorized format such that on most modern architectures, the computation of few gradient components takes almost the same time as computation of single gradient component. So it is like getting free speed up, but the advantage vanishes beyond a certain point. So the advantage is only valid as long as the cardinality of I of t is not very large. Before we theoretically derive the results, let us get some intuition as to why the stochastic gradient descent is likely to outperform gradient descent or accelerated gradient descent in terms of oracle complexity or IFO complexity. The key point is that stochastic gradient descent is better at exploiting the redundancy that may be present in the data. This means that if there is redundancy in the data, which is almost always the case, then stochastic gradient descent is better at making use of and then eliminating that redundancy. Recall that our IFO assumption gives us only the gradient corresponding to a single summand at a time. Therefore, in gradient descent, we are getting gradient of f at xt comma xi of I for every I and then only averaging it and then taking a step. there is a huge weight involved because we are concerned with using a very good approximation of the gradient as well as possible by taking average over very large number of terms. Often after we get a very good approximation of the gradient, then only we are deciding to take a step in that direction. In stochastic gradient descent, however, even with a single summand, we are taking a step. While it is not necessary that the negative of the stochastic gradient would be a descent direction, it is still a descent direction in expectation. So even with a poor approximation of the gradient, we hope that the variations cancel out over time and the function value decreases eventually. So consider an extreme example where a dataset S contains 10 copies of the subset S of sub. Then if gradient descent is applied on S, you can see that it would essentially involve 10 times more calculations as compared to the case when it was applied to S sub, because each component of the summation appears 10 times. On the other hand, observe that stochastic gradient descent would perform the same whether it is running on S or S sub. At each iteration in stochastic gradient descent, we are anyway picking a random point, and the probability of that point coming from S or S sub would remain the same. So in this example, when there is redundancy in the dataset, it is clear that stochastic gradient descent is better because it is able to avoid a lot of calculations by exploiting that redundancy. We can translate that intuition about exploiting the redundancy in the data into a real example. Consider a least squares problem where f of x comma xi I is given by square of ai transpose x minus bi. So let us assume that x is in R100, so n is equal to 100. To generate the data set, we consider three vectors a1, a2, a3 and then take ai as their random linear combination. In other words, ai belongs to the linear span of a1, a2, a3 where that coefficients are randomly chosen. This way the data has a lot of redundancy. And then we generate bi as ai transpose x star plus some noise which has zero mean and variance 0.01 square. So here x star is some fixed value that we fix in advance. The Gaussian noise with small variance is considered for demonstration, but I recommend that you run this example for higher variance and check for yourself. So we consider a dataset containing 1000 data points. The result of running gradient descent and stochastic gradient descent is shown in this figure. So here the x-axis is the number of stochastic gradient calculations and the y-axis shows the loss value. First, observe that the gradient descent converges here in only 10 iterations. However, each iteration requires n equal to 1000 gradient evaluations. On the other hand, stochastic gradient descent reaches the best possible accuracy of around 10 raised to the power minus 4 using only 10th of the data set. And this is not even enough for a single iteration of gradient descent. So in other words, you can see that the IFO complexity of stochastic gradient descent is several orders of magnitude better than gradient descent. And in fact, the gap will only widen for larger n. So this example again demonstrates the same idea. When there is redundancy in the dataset, stochastic gradient descent is better exploiting it because of its ability to work with a crude approximation of the gradient at each step. Before concluding this video, let me remark about the history of stochastic gradient descent. The first appearance of stochastic gradient descent can be traced back to the seminal paper by Robbins and Munro titled A Stochastic Approximation Method for Root Finding. And that sort of marked the beginning of the field of stochastic approximation. The stochastic gradient algorithm in particular has appeared under various names in the last 70 years or so. So let's say that phi of x is some transformation of data, such as taking DFT or extracting the features from an image. Then the least mean square or the LMS algorithm was proposed by Widrow and Hoff for adaptive filtering in 1960, where the loss was given by half of square of y minus phi of x transpose x. The LMS algorithm is nothing but stochastic gradient descent applied to this loss function. And then the LMS algorithm has been widely studied in signal processing communities till the 90s. The perceptron algorithm proposed by Rosenblatt in 1957 for supervised learning of binary classifiers. It is again the stochastic gradient descent applied to the loss function, positive part of minus y inner product of phi of x comma x. The neural network research started with perceptron and later backpropagation was proposed for efficient implementation. The support vector machines proposed by Cortez and Wapnick in 1995 for classification also used stochastic gradient descent on the loss function lambda by 2 norm square of x plus positive part of 1 minus y times inner product of phi of x comma x, which is the regularized hinge loss function. So we can see that various people have proposed stochastic gradient descent independently and for various specific losses. And there is a rich literature on each of these, with some results being rediscovered again and again. Only in the last 2-3 decades has there been some unification and general results for SGD have emerged. Now the focus is all on characterizing the performance of SGD for most general cases and without regard to particular applications. So that is all for this video. We have started looking at the stochastic gradient descent algorithm and looked at some intuition behind it. In the next video, we will look at its IFO complexity.